Okay, so this is session 5, group number 2. One question came up first, which was if you put the VI in a folder which is different to where the sub-VIs are, you will get a statement basically saying, look, I can't find this file, do you want to find it? One thing that you can do is wrap things as library files. What this is a kind of like an uncompressed zip file which contains all of the VIs. So if you go to File and then Save As, then you can almost always you do this one. So we hit continue, and then instead of just normally you just type in your new file name. But essentially what we want to do is we want to create a library file, or LLB file. So if we click on LLB, and say, what do you want to call this? We can call it ROI analysis. I'm going to create. And then it's kind of saying, look, it's going to go in this one, is that okay? We can then change the file name within this LLB file if we want to, but we can keep the same file name. If we then go to this file, so let's go to desktop. Oh, that fan's getting really loud. Session 5. So now you'll see that we've got this LLB file. So if we double click on it, yeah, this is fine. You kind of have this little manager thing. This is basically showing you the contents of that library file. But once we've got it here, we can add things into this library file. And there's, well, it's, where go we? There's a lot of kind of programs that you are going to want to actually carry these over with, especially like ones which aren't used that often. Ones that you use quite often, you can put like in you could put it just in the Labview folder in the program files if it's something that you use an awful lot, because then it's always there. But for the ones that you don't use that often, we can just take the VIs and drop them in. So let's do it directly. So if we double click on this one, we want to save it, and normally you'd have this saved to a folder, but we don't want to save it in a folder, we want to save it in this library, and at this point it will start to treat them as folders. So if we double click on it, the library file is now a folder file that we can save sub VIs into. So if we OK, we're now saved into the library file. Open this library file again. So now we have a sub VI and a parent VI. Sometimes it's kind of hard to know which one is the VI you're supposed to run and which ones are the sub VIs. So you're allowed to set a hierarchy. So if you highlight the one that is essentially the parent VI that all the sub VIs come from, you can right click on it and set it to top level, and then it gets its own space above everything else. So then you'd stick all your sub VIs, they'll all kind of pack down here, but this is the VI that you'll use when you open this library file. Then when you're in this, you can redirect the links to the library file. So right now, well, I've got this file open, so let me close this file off first, and then don't save, go away. Okay, but this one right now is pointing to some place on my hard drive in the sub VI folder. What I want to do is point it to the library file. So you have to go to replace all ballots, select a VI, and then point it inside the library file. And now this will never kind of look for a VI that's somewhere else on your hard drive. It's now looking for only within that library file. So as long as you keep saving to things inside this library file, it's a kind of a self-contained environment now. You look confused.
Yeah?
No, you're good? Okay. It's kind of like just continually saving things inside a zip file and keeping everything together. You can have lots and lots of files, and in fact, you can put just about anything in them. I use them as containers for groups of files. So then you don't even have to call the sub-VIs to have them grouped in there. You can just put them in there if you think it's something that you might use with that kind of file. So with this, we have the ROI thing. You know, we don't call it, but I could put in my custom, written ROI analysis tool. I'll never call it, but if I've got it in the same one, I'll know that if I open this library file, somewhere in the sub-VI list is my own ROI analysis tool.
Can we get now this library file?
Sorry?
Can we get now this library file?
Sure.
Because it tries to find the VI which we don't have.
Can you provide anything else? Can you provide anything? Yeah. Can you describe Kent? You just get Kent.
Okay.
Yeah, I'm sure.
By the way, I got a mail from Kjell Williamson. He said he will be coming around tomorrow or the day after tomorrow.
Chad?
Kjell, yes. So he'll be talking about the cool LEDs too. So
Is he bringing it?
I'm not sure.
Best be fucking bringing it.
Probably.
I spoke to him like 3 or 4 times without bringing the thing. No, it's the 4-unit version.
Okay.
So it's a kind of a replacement for the illumination bulbs.
For which microscope?
Any.
Okay, you just switch it around whenever we get it.
Sorry.
Sorry?
Sorry.
So you can go to any.
Should I, Mats?
Let me restart this actually. Oh crap, I can't. Oh well. For all those viewing at home, you've got this whole nice conversation about other things now. But hey, we'll keep it going, so I don't have to explain library files again. And I'll pause it now.
How did Robbie host?
Okay, so
Hey. Sorry.
that's okay. So like I was explaining to start, we've built most of this previously. Open a file, kind of show it, do some ordering. Image preloader. This time the image preloader is saving the files as well as ordering them. ROI analysis exactly the same as done previously. Then we're going to make a video file, do a simple text overlay, and then look at the outputs. So yeah, handling of the files is something that goes wrong a lot because it's so easy to make mistakes. Figuring out kind of how to strip the path and what to put where, it's very common to make mistakes, and we've seen it in all of the sessions that inevitably things happen. So one thing that is nice to do is to build your own kind of hierarchy so that when you're actually doing your analysis, things don't just go into the same folder. Open up example. No, it's not there. Let me run the VI first. Yeah, I'm just showing you kind of what the file structure will look like. So if you're actually using it right now, this is ticking along. It's doing the preload, but at the same time as preloading all the images, it's remaking all of the images. It's totally not necessary for most people. It's just sometimes it's good to have your data set like cleaned up, because we're having to open all the images anyway. We might as well clean them up and structure their file names and everything as we want them, because we're already doing half of the work, so we might as well finish it off. So, as before, we've got this real-time analysis thing. And this time we're actually doing it the correct way for a lot of data sets, which is we're not dumping the image, an RGB image, into an 8-bit bin, into an 8-bit memory location. What we're actually doing is taking an RGB image and extracting a color plane. So in this, we're extracting red. And we have multiple options here. You have all of the RGB levels, but you also have the HSL levels. So you have red, probably backwards, red, green, blue, hue, saturation, luminosity, and then value. The value is for 64-bit images, which have a fourth channel. Yeah, there's, is it HSL or is it RGB? I think it's RGBI, which is 64-bit that has a fourth level. But anyway, it does exactly like what you'd expect, but this time, rather than putting anything in this data folder, we make a new folder with all of our stuff in it. And it does it itself. We don't name anything. It's all back-end coding. In this folder, we've got 3 items. We've got all of the images renamed to be like a nice list. Very uniform. They're all in the right order now. We have a data file just like last time, which has all of our data in it. And we now have a video file, which is of the extracted color plane, but we're also running a timestamp overlay. Actually, that's probably not this one. We're running a timestamp overlay, so you can, no, it's just running up here.
For which
I'm sorry?
there's infinite.
Infinite milliseconds? We're running the same program?
Maybe the same.
But maybe not say.
Oh, you've got a different image set. Oh, yeah, no, so I can show you where the error is. So the error is that you didn't type a number in on the front panel for how many frames per second the video is.
Aha, okay.
Because it's set to 0, so it's dividing by 0. But if we just again look at the kind of file structure, the goal is for a lot of these programs that are designed to be used a lot for data sets, is you want to let the program do the heavy lifting. We don't want to have to type in. We don't want to have like, image path folder, location for all of the images after they're renamed, the location for the data file locate. We don't want to have like 6 or 7 items for the image path, for the path name, because it's not necessary. We can essentially infer it by one file path, and then you get your whole file structure from it. Oops. So if we go to the back end, that's what we're doing here. Or essentially building and stripping out everything so that we know where everything goes to and comes from. So that's kind of what we want to do first, is come up with a location to put all of our data. So I'll show you where all these parts are. I mean, most of them you've seen before, maybe not the create folder VI, but all the rest are kind of standard. One other thing that you might have noticed is that I switched out the filter, because I was looking at a lot of data sets, and it was only about half of the time where you actually needed to specify what your filter was, but there was other file names in there. So there's like text files, LEI files, etc., etc. So you actually more want to filter based on file extension than actually some, file name. But we can use this VI, which strips the file extension out to essentially filter our files. So rather than saying, look, star.jpg is my filter, you can set it to, I chose a file path. It strips that file path to tell me what the file extension is. I then add a star dot to that file extension and then filter that out. So you don't have to state, it's like whatever file type I chose, that's the file type you want to work with. If I chose bitmaps, do bitmaps. If I chose JPEGs, do JPEGs. So that all these text files, etc., LEI files are never analyzed. They only ever analyze the image type that you clicked on. It just kind of gets out of the need for having a filter name. One of the things from the previous group was, but what if you want to? What if you want to filter, like say, the confocal data? Can you add that in there? And there is a way. And what I would do is we can actually build that together first and kind of get things rolling that way. Is rather than having to actually explicitly type all of the tokens and switches with the file name, we want to make it very simple so that errors happen the least number of times. So we want to have a channel button. Okay. Rather than choosing anything, we want to create numeric control and just have something, and we'll just call it channel number. Okay, so this is, we're going to analyze channel number whatever. So this would be specific for the confocal data set. So we want to also put a switch on there which says, do I want to analyze the channel number or do I not care? Which makes it more generic. So we want to put, like a simple, either a rocker switch or a slide switch. We'll put a push button. Use channel number. Okay. So this is going to allow us to choose if we just want to filter based on the file type we've clicked on, or if we want to filter including the channel number. So then we need to write, how this is going to be used. So let's see what we've got on the back end. So like we've shown previously, channel when you create things like that, they normally come up as a double point precision, and we just want to change that representation to be some integer. So unsigned integer is fine. And we're concentrating on this section here. Okay, if we follow this line over, the ZeroPad file name VI, let's go to context help. The ZeroPad file name VI that I wrote has these inputs, and one of them is it wants to know what file extension to put at the end of this file name. So that's why we have two of these. One of them is being done for the filter, which is why it's star dot whatever file name, and one of them is being used to be fed into the ZeroPad file name VI as an extension to write at the end of the file name. So this one we can leave alone because that's going to be right, but we need to modify this filter. So we're just going to grab it and move it, and move it out here so we can kind of work with it a little bit easier. Okay, because we're gonna use a true-false button, we're gonna need to put some kind of decision tree in how this is written. Okay, so we just go to structures, and in this case we use a case structure, which essentially is it's going to allow us to put a decision onto whether this is used for the true statement or this is used for the false statement. We don't need any more cases than that. We could use a higher case structure for value inputs, etc., but true false is all we need right now. So when this is reading false, it's black. When it's true, it goes green. So it's just a standard push button. So this is false. So we need the false statement to not read the channel number. Okay, so we need to switch these cases around. Okay, so this one is true, but we actually need this one to be false. So if you right click on it, you can switch the case kind of structure so you don't have to rewrite the thing in the other case. So we want to make this case false. So that when it's false, it uses star dot plus this extension. When it's false, it's star dot plus this extension, and that feeds through. But you'll notice that this one goes white, which is the output, meaning that you can have as many inputs to these things as you want, but right now if we go to the other case, there is nothing being read into the what if the case is true thing. So we need to add some kind of statement in here. And this is where our channel number comes in. We can wire our little Boolean switch in there. So we need to take our channel number. We need to write the rest of what's written on the confocal data. So first of all, we need to change this to a string. So if you go to the string palette, string to number, and number to decimal string, it'll change this number into some string format. We're changing between two data formats. Okay, but right now we essentially have 0, 1, 2. And this always gets precursed by 0 in the confocal, and we know that, so we can build the string, or what Labview calls concatenate the string, with an extra 0. So we can take this, wire that into the bottom, create a constant on top, which is 0. So now this will output 0, 0, or 0, 1, or 0, 2, depending on what you choose as the channel number. We also need to add CH, right? Is CH for the confocal?
Yeah.
Yeah, I think it's CH.
CH00.
Yeah.
Or
CH01, exactly. So we have this concatenate thing, but we need to add some extra string to it. We can just type it straight on here, or we can put it up here. We can expand this up, but because there's no difference between it, we'll just add it straight on here. So CH0 and then this number. So if we go back to our statement, we're essentially going to want star, because we need something before this channel precursor. So we're going to need star this, star, dot whatever this ending is. So we're aiming for, what we're trying to build is star dot, oops, star dot ch00 star dot, that's TIFF, right? So this is what we're trying to build. Right, so far we've got, the ch0 and then our channel number, which is here. I haven't screwed up there, it should just be star. So we can in fact add that star here too. So now we've got this star ch00 or 01, whichever. We now need to put a star after it, and then a dot, and then this is going to pull in the file extension. So if we drag this down, we need to add something after we put in our second digit. So we need to add a star dot there. So again, we're just building a string here. We're just kind of creating a new bit of text. Okay, once that's done, we can feed that into something like this, which is reading this file extension. So we've now built this string structure. Can we do yeah, we can do it all outside, in fact. So let's keep making it bigger. This one is the file extension.
So why do you use password?
We don't have to. I can drag it inside now. I was just putting it in a place while I was building it. So yeah, we can drag it all inside. To make plenty of room. So this one should be the file extension. And then this is our new thing. Okay, get rid of this. Let's just stick that there so we know what it's doing. So now we've modified it so it'll do essentially the confocal data sets. But rather than having to type in that whole string each time, we just pick a file and choose if we want this switched on or not. And we don't have to type in any filter string. With it switched off, it just uses the file extension. With it switched on, it reads this channel number and does the rest for us. Okay, that being done, we should look at building these structures. I mean, most of you I think will be familiar with how these things work, but we can delete them out anyway, and we'll show this first. So, like I was saying, this is a VI which simplifies things a little bit by reading this file path, doing a search for where this decimal point is, and then telling us what this file extension is. Quite commonly what you'll do is actually reverse the string and then index it. So you'll just, if you want to reuse file names, for example, or want to reuse sections of a file name, the best way to do it is to take the string for the file name, flip it around, because the end is really the only defined point, and then index it based on this side, not this side. Because you can have a whole lot of strings here that vary, but this is quite regular. Most of the time it's 3 digits, sometimes it's 2, but it's quite easy to put a switch in to say, is it a true-false statement? Is this character a letter or is it a decimal place? So the way they do it is actually they search for this character, but it's not necessary. It's a bit, yeah, anyway. But this kind of file extension thing, with a lot of the file information is in the advanced section of the file functions. Oops, let me move this so it's a little bit.
So you use this strip file path twice to basically get one directory up.
Exactly.
And then add another one.
Exactly. So what we're trying to achieve is, this gives us our file path. Okay, this tells us what folder that file is in. This tells us the parent folder for where we're looking at. So yeah, we're essentially going up and down a folder structure. So we go to the parent folder, we make a new folder, or a new path name, but we have to add a special switch to the end, because without this little slash, it thinks we're writing a file name.
Mm-hmm.
Even if we wire it into a folder, it doesn't know what you mean. And because these are moderately low-level VIs, there's no kind of checks or balances or anything in these. It needs you to wire it right, else it just says there's nothing which kind of says, like, you missed a wire, you didn't do something right. It's like it's just wrong. So if you without this switch here, it will just say this folder creation fails. But yeah, so we write this folder, which is this folder here in the top level.
So you have to put this other VI there to make sure that this folder is created, the next one.
Exactly.
Mm-hmm.
So I was a little shocked that they put this in the advanced section, but again, it's in, make a folder apparently is in the advanced section at the file handling. Some of these things, have a good point that why they're here, but the create folder thing, I don't know why it's there. But yeah, this is right here, and we do it twice. One, we create a parent folder, and then we strip the path out, so we figure out like the location of this one, and then we make a daughter folder based on that. And I don't need to show you guys where these come from, because I think you guys have a grasp of where these, why you need to do this structure. It just makes your life a lot easier. If you don't put things where your actual data is, you're much better off. Actually sticking, like Leica does a real good job of sticking everything in the same folder. LEI files, data, text files, region of analysis data. I mean, it's like, why would you put it all with the images? Why wouldn't you do it like this, where you actually have, oh, I've got a data folder. That way you're not disrupting your original image files. They're all there, you never touch them. As an extra bonus, we remake all the images so that we have them all numbered nicely and named as we want them. So in last week's session, we covered kind of using the ZeroPad file name to write the files. But because we're opening all of the files, this two little section adds not that much time to the actual total program time, but might be handy to have them all renamed and numbered in a certain order. It's not necessary, you can just delete it straight out. It's just one of those kind of nice things to put in there. Okay, well that bit's kind of, you guys get this bit. This bit, answers the question of how to handle the channel number, but still keep it so that we don't have to enter a filter. The filter name always kind of gets, iffy based on like what characters you can use, etc., etc. But if we know what data sets you're using, actually hard coding is probably good. Okay.
But you said that there is also an option to like this true false thing with more possibilities.
Yeah. So you can use event structures to wire in. Like it's good. So you'd use an event structure if you wanted to wire it to like a radio button. So if you wanted to have a radio button where you have, let's say, 10 different options, you're like, this one, this one, this one, this one. Doing it on a true/false statement is long-winded. You'd have to have like a million different, and/or thingies to actually, But you can wire a radio button straight into an event structure. And do it that way. It's that's the way that you do it. Most of the time, lots of the things that you actually need to do are true/false statements. But radio,
just thinking about the possibility to keep the option of defining the filter yourself. So
Yeah. You totally could do that. You could have it exactly. You can give it an extra option with a radio button, and say, choose it, don't choose it, or use confocal. Okay, so one of the things that we want to do is build this AVI. So in Labview, AVI building is probably simpler than most other programming languages. It requires just 3 components. You make a container, you write stuff into the container, and then you close the container. Those are the 3 functions. Those are the 3 operations you need to do. The container in this case is, essentially 4 bitmaps, and if we don't compress it, that's all it is. It's a way of sticking bitmaps to each other. We can assign lots of data parameters to the AVI. So if we kind of look over, we can apply compression filters. The quality factor is. Like if you compress a JPEG, you always ask what kind of quality size to make it. That's kind of the same thing. It's like, how compressed do you want it to run this compression algorithm? So that's where the quality thing comes in. Then the other things like the has data and stuff is if you want to flow through parameters on the images into the video, because you can assign data to images, and this is kind of a way of keeping that data stream into the video. But all we really need to do is assign a path for where we want to save this file. You don't even need to put a frames per second, but I would strongly recommend it. If you don't wire it up, it'll do 30 frames per second as default. That's about it. What we get out is, it's called an AVI ref num, which stands for AVI reference number. It's a somewhat unique identifier for that container while it's open. You can read it out as a number, and then you can call it up at numerous times, but the most common way to do it is actually just use it as a wire, rather than actually just read it as an output number. So we can take this reference number, which corresponds to this AVI. If we kind of follow the wire, well, screw that. Let me put it right next to it. Where this is if we go to Vision and Motion, go to Vision Utilities, go to Files, then we have a separate little button down here for AVIs. And it's put in 2 rows for a reason. This is your standard write row, this is your standard read row. So the write row is you create it, you write stuff to it, and then you close it. So you need those 3 operations, and they have to go in that line. And the other options are when you want to read stuff out of the AVI, you have to open it, read a particular frame, you have to wire in the frame number, and then you have to close the AVI. You also have 2 other read functions. One is just get data out, because a lot of times if you want to do subsequent operations on different frames, it's not like having a file list where if you wire it into a for loop, it knows how many files there are. With an AVI, it doesn't know how many frames an AVI is. We have to actually use this, figure out how many frames there are, and then wire that in. And you also have this thing which is your filter names, and this is kind of, well, each computer and each user has their own number of like compression filters and file names, and they all use different identifiers. So I can't kind of say, you know, I'm going to encode this in Lagareth on my computer, and then your computer know what that means, because at most levels, when it's looking for a codec, it just knows where in a list that codec is. So for me, it might be codec 6, whereas for you, it might be codec 4. So you have to tell it where that codec is. You'll probably find you'll never use it, because most of the time, it's recommended that you don't compress your data if you can get away with it. It's not. There are lots of good ways of compressing your data and actually compressing, you know, in the videos, unless you have to just to like show somebody. But if we can get away with not compressing the data, it's much better, because then you don't ever have to save your output files, because the AVI is just a stack of bitmaps, which means it contains all of your original data. If you compress it, it's not the case anymore, and then you have to keep all of the original files. So yeah, so we make this container, but then we need to put stuff in the container, so it's the write frame option, and you know we're going to want to close it too. So in here, there's really only a couple of things. So we need to tell it which AVI container to write. So this is the numeric code for what container to write into. So we add that in. And the only other thing it absolutely needs is the image to put in. So ordinarily, and I'll show you over here, this will be in some kind of for loop where it's reading these images in one by one. It has to do it piecewise. We can't just create an array of images and dump them in. We have to, if we have an array of images, we have to index that array one by one and edit them and dump them into this VI one by one. And then when we're finished, we have that same reference number. It doesn't have to be from here, it can wire it from here, because it's just an identifier for this container. We then need to close the container off. If we don't close the container, you can't read it. It's kind of like the end of the file isn't written until you close this container. So it's quite important to make sure you do that. You probably can rerun the program and just close it off, but if you've got a very sensitive data set and it takes like hours to analyze it, you want to make sure that you can actually read the output file. because you can't open this VI if it's not closed. Okay, and I'll show you where they are in the sequence. So here we're just opening it over here. I mean, you can open or create this AVI at any point before you need to write it. There's no particular reason I made it over here. That was just why I fancied making it. We could have made it right before this loop. Like I was saying, the write AVI is almost always inside a for loop. Okay, and then we'll follow these data sets back and figure out where the data comes from. So what we're looking at is this thick purple line. Okay, so we're opening up all these files, we're saving them, but we don't have to save them if we don't want to. Then we're stripping out this color plane, that's user selectable color plane. Once we've selected the color plane, just like in the image preload example, we're then building these into an array in the memory. Once this is built into an array in the memory, we're kind of just flowing it through. It does the ROI analysis, but for this section it doesn't have to. Essentially we're flowing it through. Then we flow that all the way to this for loop, where this stack of images is then getting indexed, so we're handling them one at a time. For the time being, we can ignore this section. Thing that we need to look at is we've got this set of images, we're doing some manipulation to them, we're then writing them as single images into the VI, and that just keeps going loop, 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 and then when we're finished, we're closing that VI off. Now the interesting part comes in this section. So I'll show you where all the fun overlays are. So if you right click and go to the Vision and Motion, Utilities, then you have a whole section for overlays. You have lots of other functions too, but overlays has quite a lot of fun things in it, because if you wanted to show your data in presentations and things, it's quite often nice to have things written on there, and the timestamp is just one example. Putting the new scale bars on the videos as opposed to just being on the first frame of the video is another one. The ability to just draw it on there, and it puts it on every frame of the image. Having certain measurements on there, we can actually, because we're reading the intensity for a region, we can write that intensity on that frame. We can draw a box and say, look, we measured this region, this is the value for this region. We can pretty much do whatever you want. You can overlay bitmaps too, to be honest. You can overlay just about anything. However, just like in Photoshop, it treats each overlay as like a new layer. Your original image kind of hovers below, and it's treated like a locked background. You can't edit that using overlays. When you construct an overlay, you're just sticking layers on top of this image, but your original image is not modified at all. And if we didn't do this function, where we're essentially merging them, for now just take it, if we didn't do this, and we actually just did our overlays, and then read out and saved them as an AVI, it would not have any of the overlay information, because these overlays are just bits of data which are not on the image. They're kind of like, it's just a line that's hanging out in your data file. It's not part of the image. It's not until we flatten this image, until just like in Photoshop where you click on the layers and you say flatten it, does it actually become part of the image. And they can be destroyed just as easily as they're created. And I actually have one in this VI over here, where we're drawing this kind of square for the region of analysis. That little box that you draw is classed as an overlay. So if we move it around, and I can actually move it and I can show you, but every time it goes through the loop, it looks where that position of that green box is. And if we don't destroy where that green box is, it's going to keep that as a layer in this image stack. So when we go over here and we flatten the image, it'll put every single green box on the image. So if you moved your ROI around while you're trying to pick a region, it'll put like, you know, a whole bunch of green squares all over it, because we've got this whole stack of like a couple of hundred images, you know, and it just flattens them all to one image and then writes it. So when you're calling this function, you want to bear in mind what you're doing to do your analysis, because you might have to destroy the ROIs and overlays before you actually call it. I mean, it's quite obvious when you do it, because you'll have, you know, your video will look like ass. But yeah, so these are non-destructive overlays, and it's only destructive when we click merge. But yeah, there's a whole section of them, and the more kind of in-depth you want to get into your kind of presentation style for your videos, the more, you know, you'll use the higher functions. But for the text overlay, you can have control over more or less every parameter you can imagine for text. So for the text, you need to have, let me delete this and I'll show you where it comes from. So you have an image file, so this is where it's going to write on top of. You need an origin, and you need a string. So the string is what to write. The origin is where do I start writing on the image, and you know, the image is self-explanatory. But also something that you every time will need to change is the font size and style, because all your images are different sizes. I mean, writing on a 640 by 40 image requires a different font size than if you're writing on a 5 megapixel image. So you know, this is something you'll like. You just create a constant and then hard set it in the back. You can have it as a control. So if I can create control and then, you know, show it, I mean, it's a big old thing. And most of the time you don't need to control it. You know, you can set this as a constant in the back. But you know, it shows you what kind of control you've got over the exact font size and style. So we can, you know, have different text styles. The font list is a little bit limited. It gives you essentially 3 options: the application one, so that's the one that Labview uses by default. It uses the system font, so the one that your computer uses by default, and it has a user-specified font. And for that, you have to we have to wire in a code for the font that is based on your computer. So that gets more complex. Use the other ones, because it's kind of like, you know, on my computer, Windings might be font number, you know, 25, and on yours it might be font 96. So if I hard code anything in the back, it's better to use a different font. Anyway, we don't need to see that. And then the other thing is, oops. The other thing is the origin. And again, this is a little bit harder to hard fix. I'm sorry, it's a little bit harder to know what it's going to be before you actually do it. Again, heavily dependent on your image size. You can set reasonable parameters. You know, we can look at the image that's coming in here. Vision utilities. We can go into image management. We can go into get image size, and we can, you know, read in exactly, you know, how big this image is that we're playing with. And then using kind of prior information, you can decide how big an offset to make the origin. So the origins in Labview are always top left. Okay, so 0, 0 is at the top left of your image, and then it's X and Y. So it's kind of like how many go over, how many go down, and that's where it starts to write. You know, if you like, I don't know, if you're really good at kind of coupling together these things, then you can set it as some kind of ratio based on the image size. So you could be like, look, if you're 640 by 480, you know what ratio this origin should be, and you can kind of scale it for the different images, but more often than not, it's easier just to make a constant. Just tell it where it's going to draw it. And for this image size, I chose 20 by 50. It's an arbitrary number. It doesn't matter. You can put it wherever you want to put it. I shouldn't state that. Sometimes I allow it to modify itself. Most of the times I will allow it. So using this kind of using the image size will allow you to set it, but the font specifics make it a little bit trickier. When you're overlaying lines, for example, like scale bars, you can use figure out the image size and then calculate how long to draw this image, this scale bar based on the image size, so that you know that the videos you've taken, the image, the width of your image equates to 50 microns. Then it'll recalculate how big 50 microns is depending on your image size. That is a good use for that function. But okay, so we have these overlays. Are there any issues with doing a text overlay? I mean, we can go into different overlays. Let me pull up the line overlay. Oops. So this is probably the kind of second biggest one, which you'd use for scale bars, but it has very similar properties. It's just, other than having a origin point, which is a single point thing, this requires 2 data points for start and end line. So it doesn't actually ask you how long to draw the line. It just says draw from where to where. But all these parameters are data set specific. Okay, I don't think we've got anything else to cover in this VI. Whoops. Is there any questions on these kind of modifications to this program?
What's the last thing? Instead of there, we add it to default, we add it to...
Okay, so when you're kind of doing programs that have buttons, and the buttons initiate things, let's say like right now, this ROI OK button is a good example. The ROI OK button halts the data in this loop. It was stuck in this while loop until the ROI OK button is switched. But they're called mechanical operations. So just like a physical button, if we right click on here and then go to properties, it'll show us the mechanical options for this button. And just like a physical button, you can have things. Right now it's set to latch when released. So as I press and hold it, it will hold it, and as soon as I let go, it releases the latch. And they all have these kind of line graphs that try to explain that functionality. But it's actually easier just trying it. Okay. It's like, what does that button do? Switch when pressed. As you see, it's like you push down and it stays until there's another action to release it. It's like this one, I switch and it stays on. Hit it again, it goes off. Mm-hmm. That if some of your buttons are kind of wired like this, and sometimes they have to be. Like if you want a loop to keep running, or you want it to keep going from location to location, you don't always want it to latch when you push it, and you don't want it to be a single point. You actually want it to stay on until you finish, and then you want it to switch it off. Mm-hmm. That what we're doing here is, we can actually leave it in this mode because I know I clean it up. So if we go onto the button of interest, let's say, and then right click and go to invoke node, what we can do is tell it to go to its default state. So it's kind of a way of say, look, clean up all my buttons. So this button, make sure it's back to what it was supposed to be at the start of the program. So that, you know, right now if I go to this VI, if I didn't have it, then this button would stay on. So as soon as I rerun the program, it'll automatically go through without me having a chance to do anything. So it's quite good practice for the buttons to, even if you latch them correctly, to make sure you reinitialize defaults at the end. I mean, it's not necessary because technically if you chose your mechanical action correctly, it'll go to the state it's supposed to be. But, you know, it's a good, like, yeah, basically. You're just kind of trying to save your ass. Because, you know, it's kind of like this where, you know, I'm saying destroy all images. You know, it's a good kind of failsafe for me not leaving data hanging around. I could have a wire for every single iMac that I call, but at the end of the day, you know, I might miss one. Whereas having this means it doesn't matter anymore. I'm just wiping them all out. It would be nice to, I've never seen a reinitialize everything to default, but there might even be a reinitialize everything to default. And if there is, that would be a great button to use.
So in this program, basically all the iMacs stay until the very end.
Yeah.
But you might as well put the rubbish bin on every single iMac whenever you don't need it anymore.
Yep. I mean,
and in the end, you wire this arrow wire from the beginning to the end. So
yeah, I mean, it doesn't have to be there.
Can you also branch this arrow wire?
Yep. Yep. You can't connect to, but you can branch them out. Like I could, you know, as long as I'm not disobeying any rules, it'll let me branch it. So I can like say, you know, go there and there at the same time.
But it has to go back to some kind of
right. I have to create exactly. Essentially, by creating a branch, I have to then either build an error array and let it add the errors back together, or display multiple error outs. You can kind of add together two. I mean, you can just build an array and just stick them back together. Or I mean, generally.
But you cannot just wire them together.
So if I do this and like say, okay, you know, you run up here, oops, you do that, and then, you know, run through this data set to here, disable this tunneling, disable this tunneling, and then, I don't know, pick up one over here and say, oh, actually, you know, I want you to combine these errors over here. Then it'll say, what the hell's that? It's like, I can't go both ways at the same time. That's not possible.
Because it thinks that you're going from there to there, basically.
Well, yeah, because it's basically saying, look, I can't go to both these branches simultaneously and then meet them simultaneously. It's not.
But doesn't it all make sense?
No.
How you, I mean, I think you cannot do ever in Labview that you connect two data, because what is then the outcome? Yeah,
but like I'm saying, you can connect them as long as you specify how to.
Yeah.
Like you can add these together as an array. You can say, you just build an array and stick them two together. I mean, that's fine because it now knows how you want to add them together. Just adding them together means nothing.
Yeah, you can't put
you're just ramming two data. Yeah, you can't do that. But yeah, I mean, I use error lines quite a lot just because it gives a little bit of an easier flow direction. You know, you can have wacky stuff all over, running up and down and left and right, but at the end of the day, if you know which is wired together as the critical sequence, you know where it's going. And it's a very, very easy way of saying, do this before this. Because sometimes, you know...
but is there a considerable optimization slab you make in the program, or it doesn't make much optimization?
Not massive amounts.
I mean, using the principle that you are leaving the freedom, that it can decide which orders to run, it can optimize and run.
Yeah, no, normally it'll get a race condition. It creates race conditions and they're bad. Okay. You know, it's kind of like I can have something that is, you know, within one loop where I don't wire anything up, and I can have the display I can have it show the display and destroy the iMac at the same level. And it won't know what to do. Just creates a race condition. It's like, does it display the AVI first, or does it delete the iMac first? Not AVI, sorry, the image. So I can say, display image and destroy memory location for the image at the same level. If I don't wire anything up, so then you create what's known as a race condition. It's like, which one can execute before the other one? Because there's no, you're not giving any hierarchy. And Labview it doesn't know what you want to do. So in that case, it just allows the race condition. And it's similar thing with other data types. Like, you might want to, build like a particular array and then name it like something else, but you might be getting the naming from some part of an image. But, you need to make sure that one happens before the other, because they're like, well, if it took a little bit longer to analyze the image, the name for the data that you're writing doesn't hit there fast enough. So race conditions are bad in Labview, and it's not smart to figure it out. It won't say, hey, I've got a race condition. It will on some of the
strange outcomes.
Yeah, it will on some of the loops. So if you wire a loop wrong, there is such a thing as a race condition. So if you have the same data stream and then connect that to say 2 for loops, take one data stream, connect it to 2 for loops, and have different things in each of the data streams, and then wire those to some common output, it'll probably say, look, I've got there's something that we need to look at. It'll still do it. It'll just it'll probably I don't remember how I did it, but I have had a race condition error saying, look, it's fine, but there's a race condition here. So the output
will... doesn't usually happen in conventional programming.
Yeah.
Unless it's a multi-thread.
But no, it has. I have seen it. I don't remember how you invoke it. There are ways to do it. But yeah, so, I mean, there's a lot of kind of hierarchical stuff in this VI that, should give you kind of some hints to how to arrange things. I try to leave it as flat as possible, meaning it looks messy as all hell. Even if you hit clean up, I'm sure it can't clean much up, because it's still going to be messy. I mean, we're making a file structure, where to put things. And we can't even sub VI this because it's so dependent on what you're doing. There's nothing to sub VI. But things like, if you so wished, you could put things like this in a sub VI and clean things up. Same thing with this. We could clean up sections of it, but keeping it this way allows you to follow the data a little bit easier. Maybe not totally easy, but easier. And also, hopefully, I've showed you that making AVIs in Labview is very, very simple. You have a file name and an image location, and you wire them together. And that's about as complex as an AVI gets. You don't need to do anything fancy for AVIs. It really does treat them as a container for images, and that's it.
There are also free images, free programs available on the net.
Yeah.
More than one.
Yeah.
To make it no time.
Yeah.
But they mostly need bitmaps, actually.
Most of them do.
Here
Whatever you want.
With whatever.
Yeah. Yep. Yeah, the reason why the ones and stuff require bitmaps is because they don't open the images. It kind of sticks them together. Because the AVI, uncompressed AVI is a stack of bitmaps. It kind of writes a container code for a set of bitmaps. It doesn't open the bitmaps. Whereas if you've got JPEGs or TIFFs or anything else, it has to open the file. Okay. Then if there's no more questions, then I think we're good. File analysis, whatever. And